Welcome to Copernicus AI, Frontiers of Science. I'm Matilda, and today we're diving into the fascinating world of topological data analysis, or TDA, and a key technique within it called persistent homology. Adam, what exactly is topological data analysis, and what makes it such a revolutionary approach?
Thanks, Matilda. Simply put, topological data analysis is a way of extracting meaningful shape information from complex datasets. Now, when we say shape, we don't just mean things like squares or circles. TDA uses mathematical concepts from topology to identify features like connected components, loops, and voids within data, regardless of its dimensionality. What's revolutionary is that it does this in a way that's robust to noise and doesn't require you to predefine what you're looking for. Persistent homology, specifically, is a method within TDA that tracks these topological features as you gradually build a representation of the data, allowing you to distinguish between significant structures and noise.
So, it's like finding patterns within patterns, even when the data is messy? Can you give me a concrete example of where persistent homology shines?
Absolutely. Consider the work by Kyle Evans-Lee and Kevin Lamb in their 2024 paper, Identification of Anomalous Geospatial Trajectories via Persistent Homology. They used TDA to analyze AIS data, which tracks ship movements, to identify unusual patterns, specifically crop circles formed by ships. This is a novel approach to spatiotemporal data analysis, and it demonstrates how persistent homology can detect anomalies that might be missed by traditional methods. The link is in the description for anyone interested in reading more about their methods. In their study, they embedded 2+1-dimensional trajectory data into a topological space, allowing for the identification of shapes and anomalies.
That's incredible! So it's not just about finding simple shapes, but also about uncovering complex relationships in space and time. But how does it handle situations where the data is incomplete or has a lot of errors?
That's where the persistent part of persistent homology comes in. As we analyze the data at different scales, some topological features will appear and disappear quickly. These are likely due to noise. But the features that persist over a wide range of scales are more likely to be real and significant. Paul Bendich, Peter Bubenik, and Alexander Wagner addressed this very issue in their 2015 paper, Stabilizing the Unstable Output of Persistent Homology Computations. They proposed techniques for extracting a larger set of stable information from persistent homology computations, recognizing that the standard persistence diagram might not capture all the robust features. We'll link to that in the description as well.
So it's like filtering out the noise to reveal the underlying structure. Are there any limitations to this approach?
While incredibly powerful, TDA is not a magic bullet. One potential limitation is computational cost. Analyzing very large and high-dimensional datasets can be computationally intensive. Also, interpreting the results of persistent homology can sometimes be challenging, requiring expertise in both topology and the specific application domain. However, the field is rapidly developing, and new algorithms and tools are constantly being developed to address these challenges.
It sounds like the benefits outweigh the challenges. Can you tell me about other areas where persistent homology is making a difference?
Definitely. TDA is finding applications in diverse fields. For example, Anil Chintapalli, Peter Tenholder, Henry Chen, and their colleagues published research in 2025 on persistent homology-guided frequency filtering for image compression, demonstrating its use in image processing. They used persistent homology along with the discrete Fourier transform to extract frequencies corresponding to topological features, improving image compression. We can also see its use in analyzing sensor network data, understanding the structure of complex molecules, and even in financial modeling. The interdisciplinary nature of TDA is one of its greatest strengths.
That's a wide range of applications. It's amazing how a single mathematical tool can be applied to so many different problems. What about the theoretical foundations of persistent homology? Are there efforts to further refine and improve the underlying mathematics?
Absolutely. There's ongoing research to refine the theoretical underpinnings of persistent homology and develop new statistical methods for analyzing topological features. In a 2006 paper, Peter Bubenik and Peter T. Kim explored a statistical approach to persistent homology, laying groundwork for understanding the statistical properties of topological features extracted from data. Understanding the statistical significance of these features is crucial for making reliable inferences from TDA. They explored how to recover geometric and topological properties of an underlying space from a finite set of points.
So, it's not just about applying the tool, but also about understanding its statistical properties and limitations. That's crucial for ensuring the reliability of the results. Shifting gears slightly, I noticed research on using TDA in distributed computing, particularly in Byzantine-Resilient Optimization. Could you elaborate on that?
Certainly. Deepesh Data, Linky Song, and Suhas Degavi have explored the application of TDA in distributed optimization, specifically in the context of Byzantine attacks. In their 2019 paper, Data Encoding for Byzantine-Resilient Distributed Optimization, they investigated how to use data encoding techniques to mitigate the effects of malicious or faulty nodes in a distributed computing system. This is particularly relevant in machine learning, where computations are often distributed across multiple machines, and ensuring robustness against adversarial attacks is paramount. Their work focuses on how compromised nodes might deviate from pre-specified programs and how to defend against this. They have another paper in 2020 further discussing the topic in the context of stochastic gradient descent.
That's a critical application, especially with the increasing reliance on distributed computing and the growing threat of cyber attacks. It sounds like TDA is playing a vital role in ensuring the security and reliability of these systems. What are the future directions for research in this area?
The future of TDA is incredibly bright. We can expect to see further development of more efficient algorithms, new applications in emerging fields like personalized medicine and artificial intelligence, and a deeper understanding of the theoretical foundations of the field. Also, the development of user-friendly software tools will make TDA accessible to a wider range of researchers and practitioners. The integration of TDA with other data analysis techniques, such as machine learning and network analysis, will also unlock new possibilities. Claudia Landi and Sarah Scaramuccia's research on multi-parameter persistent homology also offers promising avenues for future exploration, allowing for the analysis of data with multiple parameters or attributes.
Adam, thank you for shedding light on this fascinating and rapidly evolving field. It's clear that topological data analysis and persistent homology are poised to transform the way we analyze and understand complex data, with far-reaching implications for science and society.
My pleasure, Matilda. It's an exciting field to be a part of, and I look forward to seeing what the future holds for TDA.